In this video, we are going to do an improper integral example that is both what's called type 1 and type 2. So let's look at the example, and when we do that, we'll kind of review what both of these terms mean. So I want to evaluate this integral. So why is this improper? Well, there's actually two reasons. So it's improper since... So one reason is that, well, this interval is infinitely long. So one, what's called bound, or sometimes I call it a limit of integration, is infinity. One bound is infinity. So that's one reason this is improper. But there's a second reason it's improper, and that's this function ln of x is discontinuous if you plug 0 into it. Like ln of 0 is undefined. So as a result, this whole function that I have here it's undefined if you plug 0 in. It's going to be discontinuous there. So our function, I'll just abbreviate function, is discontinuous. Discontinuous at x equals 0. When there's two reasons that the function is improper, like what's happening here, I can only deal with one of them at a time. So I am going to need to split this up into pieces. Let's split this into two pieces so I can handle each of those improper things one at a time. The 9 is just a constant multiplying the function, so let's pull that out to the front. So I got this 9, I'll put a big old bracket, and now I'm going to split up my integral. So I'm going to go from 0 to something, and then I'll write my function, x to the third ln of x dx. And then I get plus another integral that starts wherever that first one ended. So I'll just put an empty box up until infinity. And then my function, x to the third ln of x dx. So what do I put in these spots? Well, I can pick whatever I want as long as I pick the same thing in both of those spots. But, you know, I typically want to pick something small and something easy to plug in. So I'm just going to go ahead and plug in 1. Okay. All right. So I have these two integrals that I'm going to need to work out. So let's pick one of them to do first. So maybe first I'll evaluate that first one that I see from 0 to 1. So let's first evaluate that integral from 0 to 1 of x to the third ln of x dx. All right, so what's making this improper is the 0, because if I plug that in, my function's undefined there. It's discontinuous. Okay, so what I have to do first when I handle that improper integral is write my integral, but replace the thing that's making it improper, the 0, with a variable. So I'll replace it with a t. And then I keep the upper limit, the 1, and then I got my x to the third ln of x dx. Eventually, I'm going to have to take a limit here. Eventually I will have to take a limit. Let me hold off on doing that just because this integral requires a fair bit of work to work out what it is. So let's just fully do the integral, and then once we've done it, then we'll add on that limit. Okay, so I want to have you pause at this point to think about how would we evaluate this integral. So this is a bit of a review. What technique do I need to use? So I want to have you pause the video for about 3, maybe 4 minutes to try that. So pause it in 3, 2, 1, try it. Okay, so hopefully you paused it and tried it. If not, go ahead and do that now, because that is really important. We're practicing reviewing our previous methods. But let's go ahead and discuss it. So for this, we need integration by parts. Integration by parts. So for that, I got to start off by picking the u and the dv. So u, I'm going to let that be ln of x. I want it to be something whose derivative is simpler than it. And the derivative of ln of x is just 1 over x. And that's definitely simpler than it because the ln goes away. If we tried to put ln of x here, where dv is, I would have to do the antiderivative of ln. But that in and of itself requires integration by parts. So I'd like to avoid that if possible. Okay, so u is going to be ln of x. dv is the other stuff then, which is x to the third dx. Then I got to write my du and my v. Well, du would be 1 over x dx. And v, my antiderivative, that would be x to the 4 over 4. Okay, so let me put this in a thought bubble. And now let's plug in. Let's use the formula for integration by parts. So we get uv, which would be x to the 4 ln of x all over 4. I got to plug in the t and the 1 because it's a definite integral. And then minus integral from t to 1 of v du. So that's going to give me x to the 4 over 4 times 1 over x dx. All right, so if I look at this integral now, the function in here, well, the ln's are gone. In fact, I could simplify this function and just write it as it's 1 over 4 times x to the 3rd. That is definitely a much simpler thing to do the antiderivative of than what I started. And that's an indicator that integration by parts is the way to go. That is helping here. All right, so let's work this out. So this first part, I just leave it as it is. I got x to the 4 times ln of x all over 4. And then instead of plugging in the 1 and the t right now, because I'm also going to have to plug in the 1 and the t into this part when I do the antiderivative, let's just work out that antiderivative, and then I'll plug the 1 and the t into the whole thing then. So let's see, I got that minus sign, and then this 1/4 in front just stays there because it's a constant multiplying my function. And the antiderivative of x to the 3rd, well, that's just x to the 4 over 4, doing my reverse power rule. So we got this. And now I'm going to plug in the 1 and the t. So let's put a big old bracket around this whole thing. And then my vertical line with the t and the 1. Because I have to plug in the 1 and the t into the whole thing. So it's helpful to put a bracket around the whole thing, just so I don't forget that. Okay, so plugging in. So if I plug in 1, I'll get 1 to the 4th times ln of 1 all over 4. And then I get minus with the next term. With the next term, if I plug 1 in, I'll get 1 times 1 to the 4th all over 4 times 4, which is 16. Nice. And then I got to subtract what I get when I plug t in. So put a parentheses, because I'll have to distribute the negative sign in. So if I plug in t, I get t to the 4th ln of t all over 4. And then minus, with the next term, I get t to the 4th over 16. Okay, so I have this. Just to save a little bit of room here, maybe I'll move this to the side here. And now I can simplify this a little bit, because ln of 1, that's just 0. So that term just goes away. And then I can go ahead now and distribute this negative sign. So let's distribute the negative sign in to both of those terms. And doing that, well, this first fraction just becomes minus 1 over 16. And then I get minus t to the 4th ln of t over 4. And then plus t to the 4th over 16. All right, so we've evaluated the integral, we've plugged in and subtracted, and we end up with this. Now we're ready to do the limit that is involved in the improper integral. So what is that limit going to be? Well, the integral went from 0 to 1. So if I draw a number line, and I draw my interval from 0 to 1, the thing that's making it improper is the 0, because that's what made this function discontinuous. So if I get very close to 0, and I have to stay within the interval, well, I have to be approaching 0 from the right side. So I need to take a limit. Let's zoom it out a little bit. Now I have to take a limit. Take a limit as t approaches 0, but from the right side. So I'll put a plus sign. Okay, so let's do that. Let's write the limit as t approaches 0 from the right of this thing that I'm getting now. So I'll put a big ol' bracket around it. I got minus 1 over 16, and then minus t to the 4th ln of t over 4 plus t to the 4th over 16. Okay, so I got my function. I have to take the limit of this now. So this constant, the minus 1 over 16 will just stay there. With this fraction at the end, well, this one I can just plug the value of, I could just plug in. And if I plug in 0 for t, that part is just going to be 0. So that part I can handle. The trickiest part is this fraction in the middle. So for the one in the middle, if I were to just plug in 0, I would get minus 0 to the 4th times ln of 0, and then this whole thing divided by 4. Actually, just to simplify it, let's just move that 4 to the front as a minus 1 over 4. Well, so minus 1 over 4 times 0 is just 0. And then ln of 0, well, ln of 0 is technically undefined, so let's be a little careful with that. X is actually approaching 0 from the right. So the number I'm plugging in, t is approaching 0 from the right. So the number that I plug in for t is actually 0 with a little plus sign. It's actually a little bigger than 0. And if you think about the graph of ln, let me do that here on the side. Well, the graph of ln looks something like this. Where this x-intercept is at 1, but as your input approaches 0 from the right, as the value of t approaches 0 from the right, that's this part of the graph. And there, the y values are getting lower and lower and lower. They're going to negative infinity. So ln of 0 with little plus sign is negative infinity. So I'm getting 0 times negative infinity here. Okay, and 0 times negative infinity, wait, that's one of our indeterminate forms. So this is an indeterminate form. It's something I have to simplify to be able to evaluate it. And then hopefully, there's a trick to simplifying it so that I can do L'Hopital's rule on it. Okay, so I'm running out of room here a little bit. So let us carry this over. Let us carry this over to the side. Okay, so I'm going to draw an arrow from my fraction over here. And the trick is when you have a 0 times infinity indeterminate form, to move one of the terms, either the 0 or the infinity one, to the denominator. So this minus 1 over 4, I'm just going to leave it in front. So I got that minus 1 over 4. I'm doing this limit as t approaches 0 from the right. I'll leave the ln where it is. And then the t to the 4th, I'll bring to the bottom. And when I do that, it gets reciprocaled. I'm choosing to do that one because I think it's easier to write the reciprocal of t to the 4th. And it's easier for me to think about what this whole thing is going to equal. It's also easier for me to do the derivative of just ln of t versus if I had brought that to the bottom and made it 1 over ln of t. That's just a bit harder to do the derivative of. Before I do L'Hopital's rule, I have to check, well, now that I did that, am I getting a form I can do L'Hopital's on? So I plug in, and that'll give me ln of 0 with a little plus over 1 over, and if I plug in, 0 with a little plus sign into that denominator, so if I do that to the 4th power, it'll be 0 with a little plus sign, which just means it's very close to 0, but it's bigger than 0. So we already said what ln of 0 with a little plus sign is. That's negative infinity. Divided by, and if you do 1 divided by something really, really, really small, really close to 0, it's going to be infinity. Okay. I know it's positive infinity because the 1 is positive and 0 with a little plus sign is positive. All right. So I have an infinity over infinity. The negative sign, doesn't matter for that. This I can do L'Hopital on. So we can do L'Hopital. I'll just write LH for L'Hopital and put a smiley face. All right, so let's do L'Hopital. So I'll get this equals, I'll write an LH to indicate I'm doing L'Hopital's. I got that minus 1 over 4 in front. My limit as t approaches 0 from the right. Now I do my derivatives. So on the top, I get 1 over t. On the bottom, I'm going to trust that we can do the derivative of 1 over t to the 4th. I'd have to simplify this as t to the negative 4 first and then do the derivative. But if we do that, you'll end up with minus 4 over t to the 5. Okay, so I can simplify this. I got a minus 1 over 4 in front times the limit as t approaches 0 from the right. So I'll get 1 over t multiplied by the reciprocal of this denominator fraction. And if I do that and I simplify it a little bit, we'll end up with minus t to the 4th over 4. There will be a little bit of cancellation when I simplify, but I'm going to trust that we can simplify that. Okay, so we got this. This is simple enough where now I can plug in. So now we can just plug in our limit. So I can plug in the 0 for the t. So I got that negative 1 over 4 in front. And when I plug in, this part just becomes 0. And negative 1 over 4 times 0, well, that's just 0. Okay, so what we have just shown is that this fraction, the part that was hardest to take the limit of, that part just equals 0. So overall, if I put this whole thing together, I was doing the limit of this whole thing. So thus, what we get is, there was that fraction in front, that minus 1 over 16. There's this one that I just highlighted in orange that I had to do L'Hopital's on, which we just got a 0. So I got that minus 1 over 16, and then I'm going to get minus 0. It doesn't matter if I write minus 0 or plus 0, because it's the same. And then this fraction at the end was also 0. So I'll write plus 0. So overall, this just gives me negative 1 over 16. So if I look back to where we started, we split up our integral into 2 pieces. And now we just found that one of these pieces, that first piece, ended up being this negative 1 over 16. So we just got it. We just got that first one. Okay, so you might be thinking, wow, we did all this work just for one of the 2 integrals that we have to do. Like, we still have to work out this other integral. It turns out that other integral is much quicker to do. It doesn't require any sort of L'Hopital, so like once we work it out, it's easier to do. It'll still involve an integration by parts because it's the same function in here. So even when I have to split up my integral into 2 pieces, typically the first one that we do, we're going to do the bulk of the work, and the second one's easier because we've already done the antiderivative. So because of that, I'm just going to tell you what the second one ends up being. That second integral ends up diverging. And this will actually be a homework problem to work at that second integral. So, okay, so we split up the integral into 2 pieces. The first part, it was a finite value. It was negative 1 over 16. But the second one diverges. That automatically means the original one diverges. The fact that even one of these pieces diverged means the original one does also. Okay, so thus the original integral diverges. Also diverges, and that's, I just forgot to write the R. Well, I actually forgot to write the R in both of these. Let's fix that spelling. Diverges and diverges. And that's my answer. It diverges. So one of the things I want to mention about this as we wrap it up is, if instead we had done that second integral, the one that goes from 1 to infinity first, and once we did it, we saw that one diverges. If we had done that one first and saw that it diverges, we could have at that point just been done and immediately said that the original integral diverges without having to do the other part. And that definitely would have been quicker because I wouldn't have had to do both. So that would have been more efficient. But we won't always know when I split up an integral into pieces if one of them is going to diverge or converge ahead of time. Sometimes we may have to just, get our hands dirty a little bit and dive right into it and then, try it. And even if it's not the most efficient way, we can get there eventually. Okay.